Okay, very good. So it's a great pleasure to introduce our next speaker this afternoon, Jonathan Novak. So his title is Topological Expansion of Berzin-Gross-Witten and Harish-Chandra Integrals.
Yeah.
Thanks, John.
I should say that it's actually Bars, Green, Berzin, Gross-Witten, Wadia integrals. And if I don't say all that, then I'll get some angry emails. So it's I have to say. Okay. So I'm going to talk about some topological expansions of certain matrix integrals, but they're not Hermitian matrix integrals. They're unitary matrix integrals, and I think I'll try to tell you where these come from in some sort of a reasonably compelling way before I just start expanding things. And maybe one way to explain where this topic comes from is the kind of puzzling fact that when you start learning random matrix theory, there's no Fourier transform. There's no characteristic function ever in a random matrix theory class. You just don't see it, which is kind of surprising because one of the main technical tools to prove limit theorems of classical probability. And it's even more surprising because there's no problem to define what this means, right? So if I have a random Hermitian matrix, it's just a real vector in Rn square, right, for an n by n matrix. So I can just, and this trace form is just the scalar product on Rn square. So there's really no problem at all to define what the characteristic function of this random matrix Xn is. It's just the function on self-adjoint matrices defined by, expectation of exponential e to the I trace AXN. And just because we're dealing with, really just a finite dimensional Euclidean space, everything that you know about characteristic functions and Fourier transforms is true. In particular, this function characterizes, hence characteristic function, the distribution of Xn, but it's not at all used in random matrix theory. And basically, the main reason for this is because you don't really think of it as just a vector of n square real random variables, right? You're interested in the spectral data. And if you want to access the spectral data from the characteristic function of the random matrix, there are two extreme situations. One is that the characteristic function is too easy, and the other is that the characteristic function is too hard, depending on which of the classes of matrix models you're in. So if you take a Wigner matrix, where all the entries are just IID random variables, and you take its characteristic function, it's just going to factorize into a product of the characteristic functions of the entries, which doesn't tell you anything. And then, okay, the intersection of these things is Gaussian ensembles, which has, according to what I just said, have characteristic function that looks like exponential I of some quadratic form. So I wrote down trace A square, but you could have a mean or a variance. And then you have the invariant ensembles, where the non-Gaussian invariant ensembles, where the entries are correlated random variables, and it doesn't just factorize, and the correlations are very non-explicit. And so over here, it's not really clear what it's telling you. But there is something that you can say about invariant ensembles, which is, people have the impression that invariant ensembles is like e to the n trace v of x, and then you integrate it. It's not really true. Invariant ensembles are exactly random Hermitian matrices that look like a Haar unitary times a random vector written as a diagonal random matrix conjugated with this Haar unitary. And these two random matrices are independent. And so this could be anything. So for example, this vector of eigenvalues could even be discrete, for example. Right, so that actually comes up a lot in 2D statistical mechanics, like tiling models, which are basically discretizations of random matrix models. Right, so it's the world of invariant ensembles is much bigger than just e to the n trace v. And so when I compute the characteristic function of this thing, I take an expectation over these two independent random matrices. There's the beads, or the matrix of eigenvalues, and then there's the eigenvectors. And if I do the integration over the eigenvectors first, I'm taking an expectation purely over the eigenvalues of the matrix times this integral, which is playing the role of the Fourier kernel, right? So I have this. The problem is that, like, if this was n equal 1, this would just go back to the standard Fourier kernel e to the IAX. But since you have to integrate over the eigenvectors, generally, you have a kernel which is not the classical Fourier kernel. And so you sort of there's no getting around the fact that if there was ever to be a Fourier approach to invariant ensembles, you would have to, as a prerequisite, have some kind of understanding of how this kernel behaves, okay? And in particular, if you want to prove limit theorems, you're proving limit theorems when n go to infinity, which is what you would want to do with a characteristic function. This n is also going to infinity. So it's not that you have a sequence of random variables defined on the same space and you're just taking characteristic functions and taking a limit of functions. Your domain is changing. And in fact, it's this, high dimensional manifold, n squared dimensional compact Lie group that's n's going to infinity. So what you're dealing with is if this integral, yeah.
A and B are elements of non-self.
No, they're Hermitian matrices.
What?
Hermitian matrices.
Oh, I see.
Yeah.
But their size increases. Right?
Yes, their size increases.
So this function means the limit.
Yeah, exactly. Excellent question. Well, people do tend to think that way, but what you really want is you want to have some kind of control over this kernel that is somehow uniform in A and B. So you don't necessarily have to assign limit distributions to them, and I actually prefer not to. Okay.
Is that trace of A, you start a real number?
Yes.
What's the previous cycle?
You have about 5 minutes before you see it, so you can try to figure it out. Okay. So you have an oscillatory integral over this manifold of growing dimension, and there really are no existing tools for large n asymptotics of such an object, and that's why there is really no characteristic function approach to invariant ensembles. But you could sort of think about what would if you see an integral like this and you forget about the fact that you're integrating over a space of growing dimension, the first thing that comes to mind is like maybe a stationary phase approximation or something. If you've right, I thought all the physicists would jump on that one. Okay, so you could try naively to do a stationary phase approximation of this integral, right? So you just what I'll do first is I'll rescale it. So this action up here is of the same overall order as the dimension of the space over which I'm integrating. And what is the action? So if I write this down, right? If I write this down, so A and B are Hermitian random matrices, and without loss in generality up here, just by invariance of the Haar measure, I can assume that they're real diagonal. So these are the eigenvalues of these two matrices. If you multiply out this trace, this is what you get. So that's why this is a real number. Okay. And so, how do you find the stationary points of this action? It's just actually, this is the argument in the action. So maybe this is a good time to point out that this is not a function of the eigenvalues of the matrix U. It's actually a function of the squared moduli of the matrix elements. And since this is a unitary matrix, that is a doubly stochastic matrix. And this already tells you there's probably, it's not good news, right? Because the Birkhoff polytope of all doubly stochastic matrices is n-1 squared dimensional. So your reduction in degrees of freedom is negligible, which is a problem. And nevertheless, this is a linear functional on the Birkhoff polytope. So its extreme points are going to be the stationary phases that you want. So you're going to be summing over permutation matrices, right, inside the unitary group, n by n permutation matrices, probably going to give you something that looks like a determinant. And that is a famous theorem of Harishchandra from the 1950s, and Itzhak and Zubair rediscovered this in about 1980. And this is what you get. Okay, and there's something else to say here. So this is the stationary phase approximation of the integral, and this is not a tilde, it's an equal sign. And the reason for that is that when I'm doing this integration, it's equivalent to integrating over the space of all Hermitian matrices with a given list of eigenvalues, which is an n squared minus n dimensional manifold. That's an even number. And as you might suspect, that there's a symplectic structure on that orbit. And so the Dijkstraat-Heckman theorem tells you that the stationary phase approximation is exact for any fixed n. And so that's one way to prove this formula. And this is totally useless for n goes to infinity asymptotics, because here I have the determinant of an n by n matrix of phases. There's just nothing you can do. It's very opaque.
So sorry, the action has only one.
No, it has n factorial critical points. Yeah. So really exploding with n. Yeah. Yeah.
Or like all local
Yes. Yeah. Yeah.
undegenerate sort of.
Yep.
Most type.
Well, I mean, it really is kind of fairly simple because this is
Yeah,
just
yeah.
a linear form on the Birkhoff polytope, right? Yeah. Okay, so you at this stage you have nothing to. So this says analytic continuation. Unfortunately, this thing's a little bit cut off. You know, you basically are really at the level of first principles. There's no existing technology available, and so this is a good time to maybe just you have nothing to lose by making things harder. So just make everything complex in this integral. Okay, so this I replace it with a complex variable z. And my Hermitian matrices A and B, I just replace them with arbitrary n by n matrices, just in you know GLNC. And what you get, so it's somewhat like non-trivial fact, but it's true that this is a function. This depends just on z and the eigenvalues of A and B. And something happens here, which is totally not at all the case in Hermitian matrix models. UN is compact, right? So this is an entire function. This is an entire function of 2n plus 1 complex variables, namely z, and the eigenvalues of these two external field matrices A and B.
So A and B are normal,
No. If they were normal, it would be very easy to see why this depends only on the eigenvalues. It's actually true for everything. Yeah. Okay, and so this reverts to this what I'm calling Rmt Fourier kernel. So it's a function on C2n plus 1. And if I look at imaginary numbers cross R2n, which is like the phase space of these eigenvalues, this.
Sorry, the real part of z, is it 0? Or
No.
Z, any complex number?
Any complex number. So if I give you a holomorphic function and I integrate it over a compact set, you get a holomorphic function back. Okay. And what I can do then, when I'm looking at this thing kind of globally as an entire function of 2n plus 1 complex variables, I can take my I and just forget about it. In other words, z becomes a real number. And then I'm actually looking at something that takes positive values. Okay. So if I restrict this function to r cross R2n, this is a strictly positive function because it's the integral of something positive against a positive measure. Right? It's exponential of a real number against du. Okay. And so you can think about this as the partition function of a random matrix model, right? So this is it's a Gibbs measure on unitary matrices, and your z is playing the role of inverse coupling or inverse temperature parameter, and this Hamiltonian is this nice linear form that I showed you before. So your eigenvalues of your A and B are the external field parameters, which we're restricting to be real numbers here. And you sort of would have some idea from this point of view of what the large n behavior of Fn, which is the free energy of this unitary matrix model, how it might behave based on purely by analogy with Hermitian matrix models. So what you would expect is, here's a theorem that has at least implicitly come up in this workshop. So there are two ways to think about this theorem. So this is something that goes back to, as was stated, I think in Gaetan's lecture this morning, to Brezin, Itzigzin, Parisi, and Zubair, you know, sort of, right? It depends how you want to think about it. If you want to think about this as a formal matrix integral, then of course you expand this thing out, you use Wick calculus, and what you're getting is the generating function for quadrangulations. Is it actually true that this is an asymptotic expansion when n goes to infinity? As far as I know, the first people to prove this were Ercolani and McLaughlin in roughly 2001 or so. And their statement is there exists some epsilon bigger than 0. And I'm just using the quartic matrix model as an example. So this is the background GUE measure. And here's my coefficient of my quartic. If this isn't too big, so first of all, this is convergent for real part of t less than 0. In particular for t a negative real number. Then this actually is true analytically. So the free energy Fn expands to any number of terms you want with a negligible error. And these FGs, these genus G free energies you're getting, are actually analytic functions of this t. right? As long as you're inside minus e to the 0, so they actually extend analytically to a disk of radius epsilon. And they are the generating functions for genus G quadrangulations. Okay, they're absolutely summable. This is true.
Epsilon known, is it, or any epsilon is true?
No, this is actually epsilon is 1/12. Yeah, yeah.
Like in the form of.
Yeah. Okay. So, how do you prove something like that?
Asymptotic expansion. Series is not divergent itself.
Exactly.
Series is divergent, but it's an asymptotic expansion.
Okay, there are two series here. So there's a series in powers of n, and that is divergent at any finite n. And then there's each order in the asymptotic expansion, which is a function of the coupling constant, and that is convergent. Yeah, those are fine. Those are fine. Okay. So how do you prove the existence of an asymptotic expansion like this? There's, basically two approaches. So the first one is that you reduce to an integral over the eigenvalues. In other words, you're looking at this Coulomb gas and you use kind of Riemann-Hilbert type machinery. That's what Ercolani and McLaughlin did. Topological interpretation, as we mentioned already, is coming from Wick calculus. There's an alternative approach, which at least in this context, I think basically pioneered by Elise Guillenet, which doesn't rely on this at all. You can use the Schwinger-Dyson equations plus concentration of measure inequalities that allow you to control the error terms in these Schwinger-Dyson equations when n goes to infinity. And that's another way to get this same theorem. And as we discussed, this HCIZ matrix model that we're talking about is not an eigenvalue model, so you can't do this, but you could potentially do this. And indeed, there are Schwinger-Dyson plus concentration methods that you can use, so they're complicated. They're based on Voiculescu's cyclic gradient machinery. And you get a theorem that looks like this, which is a theorem of Elise and myself from a couple of years ago, which is that for each k you would like, any arbitrary non-negative integer, there's some positive epsilon k, so it depends on k, such that this HCIZ free energy expands out to order k as n goes to infinity, so it's an asymptotic expansion. And this error term is uniform on a compact box, right? So the compact box is between your z can be anywhere between minus ek to ek, so like a small number around 0 that's real, and then your external field parameters are at most 1. So actually this should be minus 1, 1 to the 2n. That's what I should have written there. Okay, and these coefficients, they are, even though they depend on n, because the number of external field parameters is blowing up, right? They're bounded in uniform norm as n overall n. Okay, so even though they're actually functions which depend on a growing number of parameters, you can think of them as coefficients in your asymptotic expansion. They don't contribute to large n behavior. And it's a nice theorem, nice result. There are some demerits to it, though, however. The argument doesn't extend to complex parameters, right? Which is the situation we initially wanted to address, because of then you're back to an oscillatory integral, doesn't apply. The thickness of this box, where you're making your approximation of the free energy, actually decays exponentially as a function of k. So the more terms you want in your expansion, the thinner you have to make it. And there's no topological description of the genus G free energies that are immediately accessible from this framework, which is a little disappointing, but still useful. It's still a useful result. In fact, this result and some extensions of it were used by Elise and Alessio Figali to prove universality for several multi-matrix models. So you can get something out of it. Nevertheless, it's not exactly as strong as you might want. So I want to come back to the complex case, and here's some further motivation for maybe doing that. So here's some other examples of where this HCIZ integral comes up. By no means an exhaustive list. So if you want to look at the Hermitian 2 matrix model, let's say, then you can go to eigenvalues, and what you get is a Coulomb gas of 2n particles of 2 different species. So they interact with each other, like blue particles and green particles. And then there's a cross interaction between blue and green, which is actually given by the Itzig-Zubair integral. Similar situation for Hermitian 1 matrix model with an external source. And then also in representation theory, this is basically due to Harishchandra, but this is the earliest version of the Kirillov character formula. This is for UN or GLNC, which is pretty much saying that the characters of a group are the Fourier transforms of its cojoint orbits. So there are many.
These two examples you stated here, they are satisfying topological regression, right? Is it a general thing that the examples you have, or this whole setting is exactly covered by topological?
So this isn't actually my setting. Yeah. The question is this covered by topological recursion?
Okay.
Yeah. Okay. So you know, and this is a conjecture. It's a conjecture which came up, you know, in quantum field theory in 1980 in this famous paper of Itzigson and Zubair. There exists epsilon bigger than 0, such for any non-negative integer I want, I can make an asymptotic expansion of the logarithm of this oscillatory integral where everything is allowed to be complex to whatever, degree of fineness I would like. And these FNGs are analytic functions of Z and the eigenvalues of A and B, so genus G free energies, which are generating functions for some unknown class of combinatorial invariants. All right, so you don't know what they are because you don't have a Wick formula. It's not a priori clear at all what they should be. And so that conjecture was around for a long time. And so here's a theorem that answers this or solves it. And so this is true. This conjecture is a true statement. There does exist such an epsilon. In fact, I can tell you that this epsilon can be no bigger than 2/27. It might be a little bit smaller, but it's no bigger than 2/27, such that this expansion holds for arbitrary complex number Z, which has modulus less than this epsilon, and arbitrary matrices A and B, which have spectral radius at most 1. Okay, so just a quick point is that you can make the spectral radius of A and B whatever you want at the cost of just rescaling this B and making it smaller. So the 1 is just a just notational convenience. And this error term is uniform on the complex variables version of a compact box of thickness epsilon, right? So a polydisk in C2n plus 1 of poly radius epsilon 1, 1, 1, 1, 1, 1, and so on. Okay, product of 2n plus 1 disks in the complex plane. And these free energies, they look like this. So this is a power series in Z in the coupling constant. And here, these P alpha and P beta are the PKs from Gaitan's talk this morning, right? So PK is a trace of your matrix to the power K. P alpha, I'm summing over all Young diagrams with D cells. And this is the corresponding product moment, right? So trace alpha 1, trace A to the alpha 1, trace A to the alpha 2, trace A to the alpha 3, and so on. Or in other words, these are the Newton power sum symmetric polynomials in the eigenvalues of your two matrices A and B divided by n to the number of rows. So in particular, these are bounded. If my eigenvalues have norm at most 1, have modulus at most 1, each of these fractions has modulus at most 1.
It's a trace of A alpha 1, but
Yeah.
A is a number just, or is it a matrix here?
A is a matrix, so this is a polynomial in several variables. Okay, so like P2, 1, A1 to AN is equal to sum of the squares times sum of the numbers. Okay, trace invariance, right? Trace invariance.
I thought that the A's are just eigenvalues of A.
Yes, they are. Yeah, yeah. But these are parameters in the model. They're not random variables. These are really the external field parameters in the model. Okay, and what is the topological nature of this thing? So the coefficients which determine this. Okay, so FNG is an analytic function of Z, which at each order D is a bihomogeneous polynomial of degree D in the external field parameters. And the coefficients, you can think of it so as a polynomial of degree D in the moments of the empirical eigenvalue distributions of A and B. That's the random matrix way to think about it. And the coefficients of this polynomial are these monotone double Hurwitz numbers that you heard about in Elba's talk yesterday. So that's the answer to this conjecture. Yeah. So that's Somehow we could stop now.
This is a
Yeah.
holomorphic function.
Yes.
And can you say something where it's holomorphic or?
I'm gonna tell you like in excruciating detail momentarily where it's holomorphic. Yeah.
Question about the
That's right. Yeah.
LA was what?
Yeah.
Alpha is the number of groups.
Right. So L of 2, 1 is equal to 2. So this normalization is giving you like this. Okay.
I'm just trying to see what.
Right. So leaning order is G equals 0. And so that is the generating function for all monotone double Hurwitz numbers of genus 0.
Right, is this, so, okay, this is the same question I asked.
Okay.
Why don't we see something involving, the eight power? At the moment, that,
Mhm.
is progress home. See something like macro.
Okay, so no, because A and B are not random matrices here. So there's a priori no asymptotic freeness that is going to be happening.
When you conjugate by A, you get.
When you conjugate B by A, by U, okay?
So shouldn't asymptotic freeness that
No, but I think I can show you something which might be along the lines of what you're asking about, which is this. There's an analogous statement for this Berzin-Gross-Witten integral, which is closer to asymptotic freeness. Okay, so this is a slightly different integral, which is AU plus BU inverse instead of AU times BU inverse. And there's also this conjecture that I showed you was also made for this Berzin-Gross-Witten integral. This is what's called the one-link integral in UN lattice gauge theory. So if you can compute the asymptotic expansion of this integral, then you can do basically arbitrary computations in UN lattice gauge theory or SUN lattice gauge theory. And so there was an expansion, there was a conjecture that, okay, I'll talk, I do want to answer Jamie's question. I'm not going to do it right now, but I'll say more in a second.
Okay.
Yeah. Analogous thing, you have a topological expansion for complex parameters. And what you get nicely is just the monotone single Hurwitz numbers. So I'll define, furthermore, what these numbers actually are as we go along. And this is the eigenvalues of C equals AB. So in particular, there's no loss in generality in just setting this B to be the identity. So AU plus U inverse is the same integral. And again, everything's convergent, right? So convergent for sufficiently small parameters. Yep.
in the previous slide, if you have the genus 0 case,
Uh-huh.
you should add again the Hertz-Chandra-Dixon formula, right?
No, it's not.
Not.
It's not right, because this is only part of the information that's contained in the Hertz-Chandra-Dixon formula. The Hertz-Chandra-Dixon formula is exact at any finite n.
Yeah, I see.
Okay. Okay, here's the proof. This is the one sentence version of the proof, so that because I'm definitely going to run out of time, and then at least you have some idea what's going on here. So stationary phase approximation does not work. Laplace approximation, when I move to real parameters, kind of works. That's the result with Elise by Schwinger-Dyson equations. And if you want to do complex parameters, you actually have to go back to really where these conjectures came from in the quantum field theory literature to begin with, which is that there is some kind of conjectural asymptotic compatibility between the strong coupling expansion of Wilson and the large N expansion of Tuft. And what that means is that you should be able to simultaneously perform these expansions in change order of summation, which is something that was, even in physics, kind of rather dubious. So there's some really nice papers of Gross and Witten where they talk about why this could potentially not be the case.
Proof for self-adjoint or approximation ones. So you're on.
Yeah, so Tufts' work is really for, Tufts has a lot of work. So
1974, we're talking.
yeah, 1974. So, okay, if I change this to 1978, then there's a then there's an expansion in this context. Okay. He did. He basically said, okay, if I can do continuum gauge theories, why don't I try lattice gauge theories?
Okay, fine. And Wilson's was for that.
Yes. Yeah. Yeah. Okay. So this is probability vigorously crossed out, and everything that we're going to be doing is several complex variables. You know, there's no benefit to thinking about this as an integral, essentially, is what I'm saying. This is a function of 2n plus 1 complex variables. And I'm kind of using this hypergeometric notation here because it actually, this is a generalized Bessel function. Okay, so I have a z and I have variables a and b, and there's two Sn symmetries. I can permute these a's and these b's, and then there's an S2 symmetry. I can swap the a's and the b's. That's what this function looks like in general. And so what do we have if we just want to get started? So if what's the only thing that I really know about this function? Okay, I know it's non-vanishing for real parameters. We talked about that. What else do I know? I know that it has the value in equal 1 at infinite coupling z equals 0, irrespective of what the other variables are, because then that's just the massive Haar measure, right? So this has value 1 in this infinite coupling hyperplane in C2n plus 1. And so what kind of an approximation are we actually trying to make if you state things clearly? So let me take the closed unit polydisk in C2n, so the phase space of these external field parameters, and I stick it inside the infinite coupling hyperplane, just embed it in there, and I thicken it out to dn epsilon. So I get this closed compact closed polydisk of polyradius epsilon 111 in C2n plus 1. So this complex analog of this box. And I want the asymptotics of Fn, a logarithm of In, on this compact polydisk as n goes to infinity, where epsilon is some fixed number. And
does this function have cuts if z is purely imaginary?
it's an entire function. So, right? So because we're integrating over compact group, over compact manifold. So this is just it's just nicest possible function of 2n plus 1 complex variables. It's extremely generic. But there are some things that you need to know. You might already see a problem here. If I want to take the logarithm of something, that something had better not be 0, right? So I know that this integral is non-vanishing for real parameters. It's a Boltzmann-Gibbs partition function. I do not know that for arbitrary complex parameters. So I don't know anything about the geometry of the analytic variety cut out by the zeros of this entire function, right? So I have this hypersurface sitting in C2n plus 1, and it's conceivable that for any polydisk I choose, for any epsilon I choose, this hypersurface and this polydisk are going to intersect non-trivially in C2n plus 1 for infinitely many n and n, in which case this conjecture could not possibly be true. I just cannot take the logarithm in any kind of a stable way. This is about phase transitions. And in order for this conjecture to be true, it must be the case that there's an absolute constant which keeps the phase transitions away, and that doesn't depend on the dimension of the system that you're looking at. Okay, so this is what you don't want to happen. This is a schematic, kind of like a real variable schematic. This is my configuration space of my external field parameters. Here's my thin box, and I have a curve, which is this hypersurface cut out by the zeros of In, and it depends on n. It evolves with n. And if I fix my box, I have no way of knowing that this curve is not going to impinge on this box as n goes to infinity. And in fact, it does if epsilon is too big. So if epsilon is equal to pi, which you actually need for some character expansions in Yang-Mills 2, this is false. This conjecture is false, and it gets used as true in papers of Gross and Madison and Kazakov and Winter, and it's wrong. It's not true. It's true in a smaller sense. If your epsilon is smaller. Okay. No, I'm not compromising on this. Yeah. Okay. So Right. So that's the issue. So what is the strong coupling expansion of the free energy? So imagine that this was true. So imagine that there was some constant delta bigger than 0, such that In is never equal to 0 on this polydisk for all n and n. And if we assume that, would we somehow get a conditional proof of this theorem based on this non-vanishing hypothesis? Maybe we could be satisfied with that. There's some famous theorems which are based on assumptions about the zeros of a certain analytic function. People kind of are willing to go forward from there. So maybe that would be good enough, but there's another obstruction, in fact, which I'll show you. Okay, so if that were true, then this free energy belongs to the Banach algebra of just germs of holomorphic functions on this polydisk. This is the sup norm of just bounded functions on this polydisk for all n and n. And the strong coupling expansion of the free energy is just its Maclaurin series, right? And written in this somewhat funny way, where I expand in powers of the coupling, which it's called strong coupling because this inverse coupling constant has to be smaller than delta. And these FND are just homogeneous degree D polynomials in the external field parameters. That's the strong coupling expansion. Okay, so they're polynomial functions on C2n. Okay, right. So what I should say here is that this is convergent. This converges this is uniformly absolutely convergent on this polydisk. So I could approximate Fn to whatever degree of approximation I would like by truncating this thing after finitely many terms, if I just take enough terms of it. But what I don't know is I don't know how that error term depends on n. So that's for each fixed n. So what that means is that if I wanted to actually do this, I need to have some kind of an idea about how each strong coupling coefficient behaves as n goes to infinity. And that's the large n ansatz, right? So the strong coupling coefficients supposedly stratify topologically as n goes to infinity. Each one of them has a asymptotic expansion in powers of starting at n squared and going down, where this FNGD is some other polynomial in the external field parameters, which first of all is bounded, right? So if you evaluate like the modulus of this polynomial evaluated on any complex numbers of modulus of most 1 is bounded in n. And this has an error term that goes to 0, right? So if I multiply this whole thing by wherever I truncate, and I look at the sup norm, the difference in sup norm of these two polynomials, so like sup norm on this unit polydisk in C2n, that should be 0. Okay, and what's going on here is that it's not clear that this is true. Okay, so you definitely know this is true, like in the world of continuum gauge theories or equivalently Hermitian matrix models, where it's really the Wick expansion. Okay, you don't know that it's true here, and you don't know what the G is supposed to be. So like, what is the topological interpretation of this expansion? And and the large n expansion was unknown in this context, and there was a lot of debate about what it could be. Right, and so the kind of the first major piece of the puzzle here is that this large n expansion does exist, and it does have a topological meaning. And the topological meaning is that these polynomials actually are counting branch covers of the Riemann sphere of degree D of genus G with a specified branch locus. So in other words, Hurwitz numbers with this extra monotonicity requirement. And I can even like tell you sort of just a little bit why there would be this monotonicity requirement. It's actually extremely simple why it would have to be this way. The 1 over n expansion, the Tuft 1 over n expansion, is an ordinary generating function. It is not an exponential generating function. There's no division by like 2 to the minus 2g factorial, right? So what that means is that if you want to be able to take logarithms and extract connected structures by doing that, you don't have a symmetrizing factor that will compensate, and your actual structures themselves must be by definition desymmetrized. And that really is the monotonicity constraint in monotone Hurwitz theory. It's a way it has to be like this. Okay, and what DeWitt and Tuft observed empirically is that something very bad happens with this expansion. Okay, so this was all just based on small number data. In the world of Hermitian matrix models or continuum gauge theories, if you prefer, this is actually a finite sum in going down in powers of n to the 2 minus 2g. Okay, it's just so there's no issues about convergence. It's just a polynomial in n square and 1 over n square. In the context of lattice gauge theories, which is where we're living, or unitary matrix models, this is never a finite sum. It's always infinite. And even worse, it converges if and only if the strong coupling coefficient you're trying to approximate using it is less than the dimension of the system which you're trying to use it on. So it's problematic. And that's another, okay, 1977, I almost had it right. It's another famous paper of Tuft and DeWitt, which is non-convergence of 1 over n expansion for gauge fields on a lattice. And you know, where is it? Blah, blah, blah. So this is talking about how it works in the continuum theory. Continue up to infinity as an essentially geometric series, but more annoyingly fails to produce the correct answer at finite n when summed. And that's exactly this DeWitt-Tuft obstruction, okay? And so they're saying, you know, we really, you know, they're saying, okay, we kind of believe that you can interchange strong coupling in 1 over n for Hermitian matrix models because at least it's just a finite sum. And they're saying here, you know, we don't really know. Must be kept in mind in this case, not really sure if you can interchange this. So this is the Tuft coupling going to infinity and n going to infinity. And in fact, they not only didn't you know, not only observe that this thing doesn't always converge, they didn't know what the Finemen diagrams were. And this was a subject of much debate. And in fact, there was a follow-up paper to this by Weingarten, where they suggested some extremely so in this paper, they suggested some extremely complicated Finemen diagrams. And Weingarten actually showed this wrong. This computation of theirs is wrong. And that if their computation was right, then you would have contributions to the leading order, which are actually not coming from planar diagrams. So there were a lot of mistakes and a lot of misunderstandings in this world in the physics literature, and it was quite mysterious. And so to put this all together, you know, what is this conjecture really saying? And this applies equally well to the BGW or the HCIZ integral. You know, analytically, it's making 3 statements, all of which are like rather strong. One is that the existence of a stable non-vanishing constant, delta, which allows me to take the logarithm of this oscillatory integral for arbitrary values of n, okay? Second is the existence of something that I'll call a stable topological constant, which says that if I take the divergent, you know, 1 over n expansion, and I take the generating function of its genus G terms, then actually I get a convergent power series for all genera G, so that at least it would be possible to make such an expansion. Okay, and that's what I'll call the stable topological constant. And then finally, there's asymptotic interchange, which is that there's some epsilon, which is less than or equal to the place where I can take my logarithm, and less than or equal to the place where I can sum up the orders in my potential 1 over n squared expansion, where actually this thing converges in sup norm to 0. Okay, so that's really what this is saying. That's what this conjecture is all about. Okay, so I'll talk a little bit about the proof, how you prove this now. But any questions about how this, at least what's going on, or good to go? Okay, it's warn you, it's going to be that's not that bad. Okay, first thing is, what are the Finemen diagrams, right? That's really one of the central questions here. So what are you actually, if there was to be a 1 over n expansion, what is it counting? So like I said, this is an analytic function. This is an entire function. And you know, its coupling coefficients are Haar integrals. Just like if I start differentiating under the integral sign in a Hermitian matrix model, I'm computing polynomial integrals against a Gaussian measure, GUE measure. Okay, these are Haar integrals. And so what you need is you need a Finemen diagram calculus for Haar integrals. And that was one of the central problems. It didn't really exist. There were some attempts to make it. It was extremely unwieldy and very error prone. And in fact, so this BGW integral where this comes in, this is the generating function for all such polynomial integrals. If I actually expand this thing out, this is a generating function for all ways I can integrate a monomial in matrix elements of a unitary matrix and its adjoint against the Haar measure. Okay, so this is correlation functions of the Haar measure. And unlike the Wick formula, where computing arbitrary correlations reduces to computing 2-point correlators, right? Just covariances. This, you have to you have to, it ends up being, this is a kind of an artifact of the representation theory of UN, you have to compute permutation correlators. It's much worse. Okay, so it's not just 2-point functions. You have to, be able to compute all Haar integrals of this form. And this is supposed to be some sort of a sum over diagrams. You don't know what it is. This is an object that's called the Weingarten function. Okay, so here are the Finemen diagrams, and this is where monotone Hurwitz numbers actually come in, and this is how monotone Hurwitz numbers were born, in fact, in order to make Finemen diagrams for Haar integrals. So this is the Cayley graph of the symmetric group SD. So here D is equal to 4. Okay, so the nodes in this graph are permutations, and 2 permutations are adjacent by an edge if you can get from one to the other by a swap. So this is the Cayley graph generated by the conjugacy class of transpositions. And just to connect up with Andrew's talk, if you look at all geodesic paths from the identity to the long cycle, let's say is up there, that is that's the Hasse diagram of the non-crossing partition lattice. It's a nice fact. It's not relevant here. And what I've done is I've introduced a little bit more information so what Hurwitz was doing was counting walks in this graph. You have to find some way to desymmetrize this thing. I've added a little bit more information where I encode the largest number, which is used in each swap. So swap with a 2, there's only one of those, is labeled 2. Swap with a 3, there are 2 of those is labeled 3. Swap with a 4, there are 3 of those is labeled 4. So in general, this is what a fragment of the Cayley graph looks like, right? There's 1, 2 edge, 2, 3 edges, 3, 4 edges, all the way around to a total of D-1 D edges for a total of D choose 2, which is the number of transpositions. This corresponds to grouping the transpositions into matrix and keeping track of what column they lie in. And in fact, these column sums are what are called the Euclides-Murphy elements in the group algebra of the symmetric group, which also very, very briefly came up in Elba's talk yesterday. And so this is the answer. The answer is that the Finemen diagrams for integrating over Haar measure are trajectories inside this graph. They're trajectories inside this graph where you have to go from the identity to whatever permutation pi you want in a monotone way, which means the labels of the edges that you are traversing form a weakly increasing sequence. Those are the diagrams, and the corresponding amplitudes are how many are there. Okay, so this is the theorem. Okay, for any, so this is where you're seeing the difference between the stable and unstable ranges that DeWitt and Tufte were seeing empirically. For any numbers d less than or equal to n, and any Young diagram alpha with pi and SD coming from the conjugacy class labeled by alpha. So this, in fact, this integral depends on pi only up to conjugacy. The 1 over n expansion is this. So this infinite series, which converges in the stable range, is counting the number of R-step monotone walks from the identity to a permutation of type alpha over all possible values of R. Okay, so that's the and these are disconnected monotone Hurwitz numbers. And okay, I'll tell you I'll just tell you now. So what it means is that there's a way to think of these things as branch covers of the sphere, but by possibly disconnected surfaces. Okay.
So in your definition there, or this formula, you have locations in R. Why not in?
It doesn't matter because because of the invariance of Haar measure, you can move the permutation to whichever, whether you want covariant or contravariant.
But for all the U's, you're on the diagonal.
Yes. Yeah.
The other one are.
Yes. Yeah. Okay. And what comes out of this is that you can write down the coupling expansion of these integrals. So I just call it coupling expansion because there's no logarithm. So these things are globally convergent. And you can do 1 over n expansion of the first n terms. Okay, so this is this DeWitt-Tufte obstruction. But now at least you know what those 1 over n expansions are. And of course, the problem here is that here I have an entire function of z. Here I have an entire function of z. And what I'm telling you about is the first n Taylor coefficients of this function. And it's just absolutely not clear, like anything could happen after that. Like all entire functions look the same, except, what are the coefficients in their Taylor series expansion? If I don't know what the tail is beyond order n, I really don't, this is not a complete description of what these functions are. And in fact, there's really no reason to assume that I could just take n to infinity and interchange order of summation, get something that would be quantitatively right. And indeed, it's not true. So if you actually want to approximate these integrals by their coupling expansions, you have to take theta n square terms, okay, which is actually the dimension of the Lie group which you're integrating over. And this is only giving you linear many terms topologically or combinatorially. So what can you do? The first thing you do, so this is, coming to formal matrix integrals now, you just set n equal to infinity, right? So that this happens all the time, right? So this is the table of the homotopy groups of the unitary groups. And there's a stable and there's an unstable, range, right? So at first, everything starts out regularly. You're integrating between the trivial group and the integers. And then it becomes wild after linearly many homotopy groups. And just you have no idea, like some of these homotopy groups are still unknown to present day. And what Bott said is maybe you should just read this table along columns instead of along rows. And so, so what that means is you take the direct limit of all the UN. So this is infinite matrices. You can have an arbitrary unitary matrix in the corner of arbitrary size and all ones after that. And that's U infinity. And U infinity's homotopy groups are actually this simple sequence. So what does this mean? It means, okay, I make, this is like, extremely formal matrix integrals. I integrate over U infinity instead of over UN. The integrand of the BGW and HCIZ integrals against du, which doesn't exist because U infinity is not even locally compact. So there's no Haar measure. And these are just ill-defined functional integrals with A and B infinitely large matrices and H an infinitely small constant standing for 1 over n. Doesn't make any sense, but we know what these things are supposed to, this is an adequate definition of what they actually are, okay? So they are generating functions in infinitely many variables, okay? So there's the Z and the H bars and then the A for this one. So this is, A1, A2, countably many A's. And here I have Z, H bar, and then A1, A2, B1, B2, and so on, going on forever. Formal power series, that's like the grand canonical partition function for all monotone walks, which start at the identity. And the partition function for all monotone walks, which go between two arbitrary conjugacy classes, monotone and single Hurwitz numbers, what those turn out to be.
Where's B in the?
Yeah, so this is this thing I was telling you about, that you can assume that B is equal to the identity. And I'm being a little bit inconsistent here because then I'm just, I'm writing it on this side and then not on this side. Yeah. Well, okay, so when you write this thing down as a function of the, so in the finite dimensional case, you write this thing down as a function of the eigenvalues of A and B. It depends only on the eigenvalues of A times B. So then you might as well take B to be the identity. Not A times B inverse. No, B might not be invertible. These are definitions. Yeah, yeah. These are definitions.
Because in the previous slide you had was on the right.
Yes. So you see it's P alpha of AB. Yeah. So I'm just saying, this is bad form. Over here, I'm just getting rid of the B. And then I had left it over here, which is not so good. Yes, that's right. That's right. Yeah. I just, I kind of knew that I did this, but then it was, how can I explain the psychology of this? I couldn't bring myself to not have an A and a B on this side. I just couldn't do it. Okay. All right. And so, what are we doing with these generating functions? There's still no topology here, though. I've kind of ruined the surprise and I told you about it. And since I'm running very short of time, I won't go through this whole construction. There's a way to go from counting walks to counting functions to branch covers. And this is a construction that goes back to Hurwitz, and you can tweak it so that it still makes sense for these monotone walks. And that's what monotone Hurwitz numbers are. So what I can do is I can write these things down as genus expansions, okay? So instead of writing walks, by definition, the disconnected monotone double Hurwitz numbers, that's what the bullet stands for, are branch covers that correspond to this walk. And the genus G here could be negative, right? Because the genus of a disconnected surface is defined by taking the sum of the Euler characteristics. So spheres are going to make negative contributions. Okay, and so I can rewrite these generating functions as sums instead of over R, where R is actually the number of simple branch points in these covers. I can write them as sums over the genus because this is the Riemann-Hurwitz formula. So this R and the G are not arbitrary; they're linked to each other by Riemann-Hurwitz, and I get these expansions, okay, which are topological expansions starting at G equals minus infinity, okay, and then I take a log, and they become connected, and they start at G equals 0. So from the physicist's point of view, if all you care about is formal integrals, this is basically a complete solution to the problem because these are the genus expansions at n equals infinity. Okay, so if you just want to work with formal power series, this is genus expansion where Fg is a generating function for monotone Hurwitz numbers of genus G. That's the BGW case, and the HCIZ case, generating function for monotone Hurwitz numbers of double Hurwitz numbers of genus G. So, and then by taking n equal infinity, this is the world of free probability. So to come back to Jamie's question, there is a certain subsection of this series, which is actually the R transform. Okay, it's the genus 0 part of this. If you take all your betas to be a ramification of a full cycle, which roughly means walks to the yeah. Okay, yeah, that's right. It's
then it would be all possible R transforms, because you're having all orders.
Yeah, I mean, so if you want to connect up with the talk of Elba yesterday, basically what's going on in here is this provides for you the potential to define our transform of arbitrary genus and much more. That's only part of the information contained in the series. No. Yeah, I don't know. Yeah, it is. It is related. Okay, so that would be sort of like a complete formal solution of this problem. But that's, you're missing out on one of the best parts of life, which is what's between finite n and infinite n, which is large n, are these approximations actually valid in some kind of a quantitative sense? And the answer is that they are, but am I over time already? So I don't have to, we can skip it. Okay, so I'll tell you a little bit about large n. This is actually quite interesting. So the first part of this is the stable topological constant. So what the formal world gives me is it gives me at least candidates. I at least know what I should shoot for. So if this conjecture is true, then these genus G free energies have to be those generating functions where I specialize them by taking only finitely many A's and B's and leave everything else the same. Okay, so H bar is 1 over n, becomes division by n, which is exactly the normalization that I need. And then the question is, can I sum this series? And the answer is yes. Okay, so there is an absolute constant gamma, like it just depends on nothing. It's an absolute constant, such that this series converges absolutely as long as you take your z less than or equal to gamma and your a's and b's less than or equal to 1. Okay, so it converges uniformly absolutely on this disk, polydisk dn gamma. So that means that you actually have holomorphic candidates for what the genus G free energies in the conjectures have to be. Okay, so this is for the HCIZ case. If you wanted the BGW case, you just get rid of the summation over beta. And so how do you know that these things converge? Well, it's a hard one result. It's a very difficult, it was hard. And so this is a theorem with Ian Goulden and Mathieu Gay-Paquet from some years ago, that this stable topological constant exists. And how do you know this? So what you do is you first look at the generating series for monotone simple Hurwitz numbers. That means that these are loops on the Cayley graph based at an arbitrary point, let's say the identity, of any given genus. So, single Hurwitz numbers are walks emanating from the identity. Double is between arbitrary conjugacy classes, and simple is loops. And there's like excruciating combinatorial analysis that you can do. It's based on join cut equations, which are somewhat similar to Virasoro constraints, which the end result of this is that you can make a change of variables and your FGs become rational functions in something related to the Gaussian hypergeometric function. And so you can conclude from that they actually, the radius of convergence of each of these series, which is actually just the critical value by Pringsheim's theorem, right? Because these are all positive numbers, is 2/27. And I always ask people about this because it's such a bizarre coincidence, and I'm forever hoping that someone will just tell me why this is true. So like, this is the type of inverse problem where I give you a number and you tell me everything that this number could mean. And 2/27, this was pointed out to me by Philippe DiFrancesco, and it's a really very strange fact. If you look at the number of finite groups of order p to the n for an arbitrary prime p, this is about p to the 2/27 n cubed. It's a theorem of Graham-Higman from the 1950s. I don't know. Okay. Okay, so that's a very, you have your targets, you have your genus G targets, and then what you would want to do is you just take your free energy and you subtract your genus G targets, some finitely many of them, and you compare analytic functions. Except you can't, right? You can't do that because of this vanishing problem. You don't know that you can stably define your FNs, and exactly because of these complex zeros. So if I can't just directly compare these things, so there's like only one option left. If I can't make a difference, then I have to make a quotient, right? So you have to work with the disconnected theory. What I can do, since I know that these guys are analytic functions in ON gamma, right? I can exponentiate them. And these are analytic functions in ON gamma again. And I just scale my entire function, which is the Itzig-Zubair integral, by the exponential of these candidates. And that is a perfectly well-defined object. And if this difference is close to 0, then this ratio should be close to 1. Okay? And here's another hard one result, which is that topological expansion of this free energy for complex data is equivalent to topological concentration of IN. Okay? So this normalized oscillatory integral, okay, so you normalize by the exponentials of the free energies that have to be the genus G free energies if this conjecture is true. You subtract 1 and you say, how big is this difference in sup norm? And if it's OK of n to the 2 minus 2k, where this is allowed to depend on k, so for each fixed k, as n goes to infinity, then in fact you're done. So topological concentration is equivalent to topological expansion. And there's a reason for this, which is a good reason, and I'll show you that reason. Maybe you can already see why it is. So let's go back up to n equals infinity. And what is the topological expansion? Okay, if we're working with formal power series, I don't need to take the log. I can say that my topological partition function, I think that was a term that was used the other day. This is a topological partition function. It's exponential of the generating series for connected coverings, which is the generating series for possibly disconnected coverings. And what I can do is I just factorize it, and I move all the data of genus at most k to the other side of this generating function. So I'm just like dividing by a formal power series. And what I get is I get the generating series for disconnected covers. So this is wrong. This is supposed to be G equals k plus 1 to infinity. These are not, that was a copy paste error. Okay. And since I'm, at least removing spheres, which are genus 0, and those are the only things that have negative Euler characteristic, right? Or I forget which way it goes. Which one's Euler characteristic? 2 minus 2G or 2G minus 2?
2 minus 2.
So the only ones that have negative Euler characteristic, okay? And so when I expand this out, I get surfaces of genus k plus 1, okay? So this formal order symbol in this ratio of generating series is O of h bar to the 2k, okay? And my h bar is 1 over n. So that's the concentration formally. It's the fact that when you multiply through by a signed sum of surfaces of genus less than or equal to k through all surfaces, you're going to kill the surfaces of genus that are less than or equal to k. That's exactly what this identity is saying. And you notice that here I have an h to the 2k, and here I have, this is n to the 2 minus 2k. So this estimate is n square worse than the estimate from the perfect world. Okay, and that is exactly the role of finite n. So if you remember at some point I told you that if you actually want to have a true approximation of In by its coupling expansion, you can't just take n terms, you need order n square terms. And that's where this extra power of 2 comes from. Okay, so finite n, like, introduces some stuff that you have to control because you're going out to order n square instead of just out to order n. But the extra error that it gives you is not enough to actually disrupt the conclusion of the theorem. Okay, so that's basically it. And I just wanted to maybe make a total fool out of myself by saying something extremely hypothetical, which is a possible way to rectify in various situations the gap between formal topological expansion and analytic topological expansion. And it's this 3-step process. So what you have to do is find a good holomorphic approximation of the partition function. Okay, so never ever take a logarithm, right? And we got lucky here because we were doing unitary matrix integrals. It starts life as an entire function. There are various ways that you could try to do this for other matrix models, which I won't go into. Step 2 is use topological recursion to check that your genus G free energies, which are formal power series, are actually analytic objects. Typically, this can also be done with Schwinger-Dyson equations. So you have candidates, and you can't compare your candidates to your holomorphic approximation by subtraction exactly because of phase transitions. But I think it's an important point that topological expansion is equivalent to topological concentration. That's a general principle. Okay, so you could try to prove topological concentration, and if you can do this, then you will get topological expansion as a conclusion coming out of this. So that's one possible way to try and go from formal to analytic and rectify the two. Okay, so okay, that's it.
Thank you. Are there any questions, other questions?
So reconciling would mean that those whole series.
Yeah.
How you put in the function what's it a function of? There's a set.
Right. So in the context I was talking about, it's Z and the eigenvalues of 2 external fields.
Right, and then you assume eigenvalues have a limit.
No, I'm just assuming that they're confined to the unit disk. And from there on, everything is uniform in them. All estimates are uniform in them. Yes.
Would it be better just to assume that you measure?
No.
Okay.
No, it wouldn't.
That seems to me as a fighting chance. Whereas taking something.
We don't need a fighting chance. We just won. So, yeah. Well, it's a comparison of 2 functions, each of which have an exploding number of variables, but finite. That's why it's several complex variables. Yeah.
Questions or comments? Just one question. So at the table, both periodicity table, you don't use both.
No, not at all. Yeah, it's just a heuristic. Yeah. Yeah.
There's as a weird.
Yeah.
Never done before, so
Yeah.
that'll be more really. Question?
I was going to ask essentially.
Oh, I see.
Yeah.
Okay, so.
Actually, maybe to ask him.
Sure. Yeah, of course.
How much?
Actually, not too bad. So not too bad. You see, one of the key things that happens here, this slide is as good as any other, is that the external field variables get normalized by n to the L of alpha. So that's why I'm assuming that they lie in some compact set of fixed geometry in a space of growing dimension. For example, the unit polydisk. It could be a polydisk of any fixed polyradius, even though the number of radii is going to infinity. That means the absolute value of each of these complex numbers is always at most 1. So for many purposes, this is the variable that matters. Okay, so there's a lot of this can be reduced to single variable complex analysis.
So must be some way. That's what does. Is that
Yeah.
This says it just those A's
Right.
are sampled from some
Yes.
probability measurement, some other one. We have the free out.
I'm doing it this way for you. I'm doing it this way so that you can take whatever samples you want and send them wherever you want. Yeah, this is a user-friendly formulation.
Any other questions? So questions from the Zoom audience? Maybe? Oh, so let's thank Jonathan for giving
Okay.
the longest talk. Okay, very good. So we have a day. So now we can, yeah.
Dinner plan.
Yeah,
I already sent the email to everyone.
that's right. Yeah. So is it at 6?
6.
So how we gonna go